Okay, so if you want to read more about the fluorescence and how all this mechanism works, you can read more on this Frank codon energy level diagrams, as well as how the solvent actually affects the energy levels for your fluorophores. Next. So let's talk about the epifluorescence. Sometimes you encounter this term epifluorescence. It simply means that the same objective is being used to collide the and to excite the molecule as well as to collide the emitted light. Right? And it's a type of reflected light microscopy. So if you recall, when we talk about your DIC or bright field, phase contrast, they are based on transmitted illumination, right? You have a sample here, you pass your light through, you detect on the other side. Right? That's the transmitted light microscopy. On the other hand, fluorescence, when you hit your sample, your fluorescence, they don't just go in one direction. The fluorescence comes out from all directions. So basically, you can collide back the fluorescence through the same path. Right? This is how most of the fluorescent microscopes has been designed. So over here, you have a light source, and typically you have an excitation filter to select the wavelength that you want to use. For example, you don't want the UV, you just want this particular wavelength. So you have an excitation filter that blocks out the rest of the light. You have a dichroic mirror. The dichroic mirror specify that below a certain wavelength, it reflects the light, so it goes through the objective, gets focused on a sample, right? Fluorescence happens, and you collect back the same through the same path. And because there's a Stokes shift, the wavelength is now different. It now gets transmitted, right? Because it's above a certain wavelength, dichroic mirror will transmit the light, and it hits the second filter, which is the emission filter, that further selects the wavelength that you want to collect your light from, and finally the detector. So that's in a nutshell how the basic fluorescent microscope works. And on a basic fluorescent microscope, these three elements are usually in a particular cube. We call this a filter cube. So they are kind of fixed. So if you want a filter cube for, let's say, GFP, you can only do green excitation. If you have one for DAPI, then you have to change this filter cube to one that can image, for example, DAPI. So if you notice, if you go to our website, NOBIC website, there's a section called microscope fluorophore selector. And if you look at our microscopes that is available, let's say in NOBIC, we actually categorize the filters into filter sets with fixed excitation and emission pair. This means that all these three elements are fixed, right? But sometimes, let's say you have special fluorophores. For example, you excite the fluorophores in green, but you want, because the Stokes shift is very long, you want to collide your fluorophore, let's say, in red, right? In a standard filter, you can't do this, right? Green, you collide it in yellow. But if you want green and you collide it in red, then you have to look for microscopes that have these three elements separated, right? So these are highlighted in asterisks here, right? So all these microscopes have this flexible combination where these three elements are not in the same filter cubes, right? But for the very basic one, usually they are on the same filter cube. For example, your Nikon. So if you go into one of the microscopes, you will sometimes see filter sets and all these numbers, right? You will see usually three sets of numbers. These are the wavelengths of the excitation filter, the dichroic mirror, and the emission filter, right? So just to quickly cover these filter sets and how you can read them. So let's say you have a GFP filter, right? So from this spectrum, you have this GFP excitation spectrum here, and then the GFP emission spectrum. And here I give it, let's say you have, on the microscope, you have a xenon lamp, right? The xenon lamp has excitation that covers a wide range. So first you have your excitation filter. So your excitation filter will block out all the light that is not within this band, right? Will just allow this wavelength to go in and hit your sample, right? And your dichroic mirror will only reflect the light that is below 495, which is what you are using, right? This is your excitation wavelength. The dash 40 means is plus or minus 20, right? This 466 is a center wavelength, plus or minus 20, right? The whole bandwidth is 40 nanometers, right? So when your fluorescence comes back, because your fluorescence has a Stokes shift and is shifted about 20, 30 nanometers to the red, right? It passes through your dichroic mirror because your fluorescence is now above 495. It goes in, hit your emission filter, which then selects the wavelength between this band, right? Centered at 525, this whole bandwidth is 50. So that's how your fluorescence microscope works. And this is what happens when you select different filters, right? So this is, but in normal circumstances, you don't have to worry too much about the numbers, right? If you use a GFP filters, basically you can use it for any green dye, right? Your Alexa 488, your Fixie, Fluorescence, right? So if you want to use a red dye, you can then choose maybe a MRP channel, then you can image those. You only need to maybe take a look at the numbers if you are using dyes that are not the typical ones, dyes that have very long Stokes shift, like you excite here, but your emission is somewhere at the rate. That is when you need to understand whether the microscope are able to handle such dyes, right? Okay. So let's talk about multicolor imaging. Right. So sometimes when we train users on the microscopes, they are a bit confused about when it comes to multicolor imaging. There's actually two modes of imaging. The typical one, right, is the sequential imaging, meaning that if you have two dyes and you want to excite it using the blue or the green, you basically just excite the blue first, collide the blue, the light, and you switch the filter cube to the green one, and then you excite it with the green laser or light, and you measure the other channel. So that's called sequential. Typically this works, but however, if you have some samples that move very fast, meaning that when it switches the filter cubes in that time frame, you are monitoring something and it moves. So before you capture let's say the green one, it moves. So your image will not be the same between the blue one as well as the green one. That is when you will need to do simultaneous excitation, meaning that you excite with the blue and the green light. However, because most filters or most basic filters, they only allow one particular wavelength to go through, but you will need usually special filters, either called in this case, it's called the dual band filters. It allows two wavelengths to be able to pass through, and the dichroic mirror allows two different colors as well, and the emission filters also. But one thing to take note, although this is kind of fast, right? But if you look at this example here, I have a green dye and an orange dye here. If you excite both at the same time, you'll notice that your green emission, right, can leak into your orange channel because you're collecting them at the same time. If you're collecting your orange emission here, you'll see that you tend to collect some intensity that is coming through from the green, right? This is sometimes called bleed through or crosstalk. So this is something you need to take note of, especially if you have a high expression level of the green dye. So when you try and try and look at your orange channel, right? The high expression of the green dye might actually contribute to quite a substantial amount of the intensity that you collect. Right? So just this is something to take note. Unless you are imaging something very fast, I would suggest just stick to the sequential imaging. Right. So we have basically covered one of the probably the most important fluorophore properties that a user would want to look at, which is the wavelength, right? So that the wavelength determines the amount pairs of dyes that you want to use for multi-color imaging, and also whatever diffuser sets that are available on your microscope. There are a few more properties, the fluorophore properties, that I would like to quickly cover, so that when you go to a certain website, let's say your company that you want to select a dye, sometimes they give you terms like extinction coefficient, right? They have the brightest dye. So what does brightness mean? What is molecular extinction coefficient? Sometimes they give you quantum U, and they also tell you, oh, it's more photostable. So what's photostability? So I'll cover these two. Lastly, I'll talk about a little bit about lifetime, which is not usually used in standard fluorescent microscopy. So let's first talk about brightness. So brightness basically is it is a component of extinction coefficient. So let's talk about extinction coefficient first. So extinction coefficient, if you remember your chemistry, this is the Beer-Lambert law. Your absorbance is equivalent to this extinction coefficient, which is a constant, multiplied by your concentration of your dye and the weight and the light path. So this is when you put your cuvette into your UV spec, right? The light path is usually 1 cm. But that's not important. Important is the extinction coefficient is high, your absorbance is high, meaning you are able to take in more electrons, right? Take in more photons for excitation. Next, even though if you absorb more photons, it does not mean that you emit more photons, right? Quantum use, a fluorophore with a high quantum U would be able to have a ratio that is, for example, the quantum U is the ratio between the number of photons emitted divided by the photons absorbed. So if you have a high quantum U dye, meaning that if you excite the dye with let's say 10,000 photons, you will get back maybe 9,000, for example. So that's high quantum U. But some dyes have very low quantum U. Maybe they only give you back 50% of the amount of photons that it absorbed. So when we put all these two factors in, and what we are interested in is the fluorescent intensity, right? We are always measuring how high our signal can go. And that's the factor of, let's say, an instrument factor. Just take it as this is maybe how much light is being lost in your microscope, right? It's a factor of how much light you put in. And the rest is basically just about quantum U and the molar extinction coefficient. So we could simplify this to a term called brightness, which is basically the multiplication of two properties, which is the quantum U and the extinction coefficient of your fluorophore, right? So that's how we measure how bright our fluorophore that we use is. So the brightness is a number, right, that you can use to kind of tell yourself, okay, is this dye much brighter than the other? Next, photostability. So if you notice, if you have used a microscope, let's say to monitor your sample over a period of time, you'll notice that after the initial scan, and maybe if you later on you scan it again, you'll see that the image quality or the intensity drops. So this is because of a phenomenon called photo bleaching. Right? Photo bleaching is the irreversible destruction of your fluorophore due to chemical reaction, right? And what you observe observe on your microscope is a fading of the fluorescent signal. So what exactly is this photo bleaching? What is this chemical reaction? And in fact, photo bleaching is poorly understood. We know it's dependent on the intensity and the duration of radiation. But a very popular or kind of accepted mechanism is based on again, this principle. So remember that if you excite your fluorophore for a long time or using high intensity power, some of them will go to the triplet state. And in the triplet state, right, it can react with your oxygen. So basically our oxygen that we breathe is actually triplet oxygen, meaning that it has actually two electrons that has the same spin. So it has a triplet oxygen. It does not mean that it's reactive, but just that the triplet oxygen will actually react with the excited triplet state. So the triplet state will then go back to the ground state. But the consequence here is that the triplet oxygen is then converted to singlet oxygen. And this singlet oxygen is very, very reactive. Right? It will tend to react with anything that's around it. Right? So is this single oxygen that reacts with your fluorophore that chemically change it. So basically it destroys the fluorophore, which is why you have photo bleaching. And on top of that, this single electron is able to react with any biomolecules in your cell. For example, your DNA, your proteins, which is why it's also cytotoxic to actually image your let's say your live samples using high intensity or prolonged radiation. So what can we do about photo bleaching? There's a few ways you can kind of reduce it. You can't remove it completely. Right? The first thing is if you are buying a dye, right, you could try different dyes, right? So if you take a look at some of the dyes that we have in the market, for example, the Alexa dyes, right, it's pretty photostable. So over a period of scans, right, the intensity doesn't drop as much as, for example, your Fixie, right? So for the far rate, the best one we have is Alexa 647. Right? If I'm using sci-fi, the kind of like the old or the classical dyes, you'll see that sci-fi photo stability is not that good, right? So if you can't change the dyes that you are using, then probably you can lower your illumination intensity, or you can minimize your exposure time. And in some case, when you are searching for your cell, you can limit the area that you want to expose your sample to light, right? And of course, some people use multimedia with anti-fade protection. So there's this link where you can read about the anti-fade. So basically, what's inside the anti-fade is some chemicals that basically react to the oxygen species that I talk about, the single oxygen. So it scavenge the oxygens, the single oxygen, so that it doesn't cause any or cause too much damage to your fluorophore. Right? Okay, the last part I want to talk about for the properties of fluorophore is the lifetime of your dye. As I mentioned just now, in fluorescent microscopy, we basically don't measure the lifetime, or we are not doing, or we are actually not so concerned about the lifetime of the fluorophore. But I would like just to cover this property because there are special techniques that allows you to measure the lifetime of the fluorophore, and that's based on a microscope called fluorescent lifetime imaging microscopy. Of course, you need specialized equipment for this. So what is the lifetime of a fluorophore? So if you remember the electrons after excitation, they will all sit here, right? So when the electron goes back to the ground state, they do not go back at one shot, right? Over a period of time, some of them will start to come down, and there will be a kind of like a decay, right? So if you excite it, right, some of them starts to go down, and over a period of time it disappears. This period of time, as I mentioned, for fluorescence is about nanoseconds, right? So over here there will be a lifetime. So the lifetime is very different between each fluorescent dyes. So in film, basically we are not concerned about measuring the intensity or the wavelength of your fluorophore. Right? We are not concerned about whether you see the green channel, the red channel. No, we just concerned about measuring this number, which is the lifetime. And the lifetime can actually distinguish fluorophores that have very similar wavelength, for example. Right? So this is something to take note. So just to summarize the first part, which is the properties. So I covered the wavelength, the brightness, the photostability, as well as the lifetime. And for the last few slides, I'll go through the organic dyes. So before we go to the organic dyes, I just want to say that the types of fluorophores that we have are usually divided into three types: the organic dyes, the quantum dots. Quantum dots are usually inorganic matters, right? And then they coat, but they are pretty big in size, right? Then of course, most of you, if you are doing live cell imaging, you might be familiar with the fluorescent proteins, which I will cover in the second part of my talk. So just to say a few notes about quantum dots, they are actually very, very bright and very photostable. You can actually functionalize maybe the outer shell here to be able to target certain molecules, but it's kind of limited. Right? And because of the big size, right, 15 to 20 nanometers, they are pretty much bulky. And also, if you are doing things like live cell imaging, you have to think about how to get these quantum dots into your cell or into your organism. So it's not that straightforward. That's why it's not that popular compared to for example, organic dyes, which are much smaller, as well as the fluorescent proteins, right? So that's just one slide for quantum dots. Doesn't mean that it's not useful, but it's usually not used that much, at least in molecular cell biology. So the last part is the organic dyes. So what are organic dyes? Organic dyes are basically just small chemical dyes. You might be familiar with your Fixie, which is fluorescein, Trixie, that's your rotamine, and you have your classical, the Psi3, Psi5 dyes. Right? These I usually call them the classical. Some people call them the older dyes. Nowadays, a lot of companies sells dyes that are basically modification of Fixie, Trixie, or even Psi5 dyes. Right? So they basically just change some of the side groups, that add some stuff here, and they come up with dyes that are considered to be brighter and more photostable. Right? The most commonly one you might encounter is the Alexa 4 dyes from no longer molecular probes. Now it's been brought over by Thermo Fisher, and there are other dyes like the DY Light as well as the Arto dyes. Right? These dyes, in their native form, they are non-targeting. Non-targeting meaning they don't attach to any of your biomolecules. Right? They need to be functionalized, maybe with a reactive chemical group, to be able to react with molecules. Right? And as well as if you use antibody, you will know that the antibodies are usually attached with all these dyes. Right? For example, you can attach your Alexa 4647 to phalloidine. Phalloidine is a peptide that binds very strongly to actin. So basically, using this combination, you are able to label your actin filaments with Alexa 4647. Right? And of course, your immunostaining, where you use your antibody, and then you attach a secondary antibody that is attached to a dye that you want. Right? So that's how you actually use the organic dyes fluorescent imaging. And you can actually go to the Thermo Fisher website. There's a lot of resources here, like a lot of things you can read up on. Just want to say a few words that, for example, the fluorescence spectral viewer, the fluorescence spectrum that I showed you in a few slides earlier is generated from this website, right? And if you go to the molecular probes handbook, right, there are chapters of chapters that are related to dyes, the probes. So if you have a specific question that you want to ask, for example, if you want to look for lipids or cell tracer, or probes that detect, for example, certain calcium or even pH, you can actually go up and read about them. It's too much for me to cover all this because there's just too much probes out there in the market, right? But last few slides just to cover, for example, there are DNA stains. The popular ones are DAPI, the Hosh dyes. The difference basically is usually people prefer Hosh for live imaging because it's cell permeable and it's less toxic. Right? Of course, when you look at DAPI, it's supposed to be cell impermeable, but if you add more enough DAPI, actually you can actually stain your live cells, right? And then there are cells that are like these two are in UV, right? So Yo-Yo and all their series like Bobo, Toto, or whatever, they have a different wavelength. The only issue is cell impermeable, so you probably have to permeabilize your cell. For example, you need to fix your cell. But sometimes these are used for detecting extracellular DNA. For example, in bacterial biofilms, they have matrix that contains DNA that's outside the cell, extracellular. So you can actually use Yo-Yo dye to stain them. There are other dyes that in the far right, for example, JAK5, right? If you want to look for DNA stains that are not in the UV regions. Membrane stains, common ones are these DIO, DIL, DID. Right? They have different wavelengths. They partition into your membranes. When they bind to a membrane, the fluorescence increases. Right? Then there's some special dyes here. The FM, this is my kind of my favorite for staining bacterial cells. I work more with bacterial cells than eukaryotic cells. But this FM dye it stains my bacteria very, very well. But if you take note, right, the excitation and the emission is very far apart. Right? This is what I call it the long Stokes shift dyes. And if you stain your sample with this dye, and if you go to a very basic microscope, you actually can't image it because the filter sets are fixed, right? It's fixed for low Stokes shift dye. So if you want to image this dye, you have to go to a microscope that has a flexible excitation and emission filter setup. Right? Otherwise, you can't image it. Okay. There are other popular dyes like cell mass, right, which stains your eukaryotic cells. So these are just a few examples, right? So I would like to end the first part of my talk this morning here. So if you have any questions, you can ask now, or you maybe post your question in the chat, right? Let's wait a while and see whether we have any questions from virtually as well as from the audience in conference.
Pretty good.
Yeah.
So actually I realized the DAPI after like I image for a while, it will turn into like green color.
Green color.
Yeah, like from blue, then after a while it will like become green. Is it?
Green meaning you switch your filter from DAPI?
No. It's like the image of the nucleus.
But your image of your nucleus is based on the DAPI channel.
Yes.
So it can't turn green because it's being colored with blue.
Yeah, it's supposed to be blue like initially.
Yeah.
Then after a while, then it will like become green. I don't know. After like long imaging.
So your image will become green.
The nucleus will become green color. You never experienced.
Maybe we can talk about that later because I mean if you're talking about the digital imaging where you see on the computer, the color can't change because it's actually fixed by you. You can actually give Dapi, let's say, a red color.
No, I didn't change the color.
Yeah, so that's why I don't understand why it will become.
Yeah, I also don't
Yeah,
understand.
so probably we can have a look.
Okay.
Okay, so there's a question in the chat. Is there any dyes recommended for measuring the microcurrent across the OYA? So I think there are some potential dyes. I mean the channel potential dyes, but I'm not very familiar with that. Let me see. Yeah. So there's an answer here. Fluorophore. So here I think there's a probes for membrane potential. Yeah. And what one of the audience has said, so there's positron and botron. Yeah. Okay, thank you very much, Suresh. Right. So is there any more questions? Right. If not, you can also ask me later on when I cover the second part. So maybe we take a short break and we maybe about 7 minutes. We come back at about 10. Right. So at 10 a.m. then we will start the second talk.